A cone-shaped drinking cup is made from a circular piece of paper. So they have a piece of paper here, radius r, and they cut out a sector and joining the edge CA and CB. CA and CB. You have a freedom to choose to cut how much you like. For example, in this case, they cut off this, and then they join CA and CB. They get this figure. So the more you cut, you might get a higher cup. The less you cut, you might have a wider cup, but it's shorter. Let me draw the figure. We have a cone. So this is our cup. You know that they glue this length to this length. So they glue it along this. So this is our radius big R. And then you have a height of the cup. The height 8. And say the smaller, this one, R. This is the radius R. You can compute the volume of the cup. Volume equal to 1/3 pi r squared times 8. So this is a volume and we want to maximize it. Find the maximum capacity of such a cup. Maximize this volume. So we want to maximize that in terms of R. Radius R. So let's do this. You have this right triangle. So you can write down R and S in terms of the radius big R by Pythagorean theorems for this right triangle. You have height square, small radius square equal to big radius square. Now we note that the height and the radius are length, they are all positive. Height, radius bigger than 0, and we know that this one is at most radius, so everything's bigger than height square and also bigger than radius square. So if I do that, I get height square less than big radius square. You can square root both sides, they are own length, so we don't need absolute values. And similarly, you have small radius square less than big radius square. Radius, small radius less than big radius. So the condition we have for our height and radius is 0 less than height, radius less than big radius. So they are both on the interval 0 to big R. Now we need to write out this with one variable away. Height square equal to big radius minus small radius, square root both sides. You have height equal to square root of big radius minus small radius square here. Now I can rewrite the formula of the volume in one variable. Volume equal to this. I say volume is V 1/3 pi radius square and height equal to square root of this. This is our volume function in small radius because big radius is fixed. Now we have the function. We have the interval for small radius between 0 and big radius. Now let me compute the derivative to get the critical point V prime R. Here we have a number pi over 3, take it out, and I use product rule. 2R square root R square minus small r square. And the second one, R square times this one derivative. So 1/2 times 1 over square root r squared minus r squared times minus 2r. So remember that you can think of this as r squared minus r squared power on half, and then you get this. Now pi over 3, the first terms I keep the same. The second terms we can cancel out with 2. So what we have is square root r squared minus small r squared. R squared times small r squared. Here we have minus r cubed. So this one is pi over 3. We can do common denominator. R squared, small r squared, 2 small r, big R squared, small r squared, minus r cubed. R, small r's in common. We can group it so that it helps us to solve for v prime equals 0. Small r, inside you have 2 r squared minus 2 r squared minus r squared. This one equal to pi over 3, 1 over square root r squared, small r, 2 big R squared minus 3 small r squared. So now this is our v prime. V prime equal to 0 if this one is 0 or this one is 0. V prime r equal to 0 if and only if small r is 0, which is not the case. Impossible, no. Or 2 big R squared minus 3 small r squared equal to 0. So this case gives us 2 big R squared equal to 3 small r squared. Small r squared is what we need to find because this big R is fixed. 2 over 3 big R squared. Small r, they are all positive number. Square root both sides, no absolute value there. Square root 2 over 3 times big R. This is our critical point. Now let's draw the table. We have R from 0 to big R. That is the condition we are working with here. V prime, which is this one. So here's our V prime. V prime equal to this. So critical point, this critical point, square root 2 over 3 times R. So you see that is 0 here. And we have the volume. So now you see this formula. So here's V prime. Let me write more clearly. V prime equal to this whole thing. They are all positive here. So it really depends on the side of these terms. So these terms, I can rewrite that a bit. So this depends on R squared here. Minus 3. So I put 3 out. Inside 2 over 3 big R squared minus small r squared. All these terms are positive. The last terms can be written as square root 2 over 3 times r minus small r times this one but plus. Here you see that they are all positive everywhere else except can be negative because of these terms. So when small radius here less than this number, then this term positive. I hope you can see that clearly. This term is positive when small r less than this. When small r less than this term positive and negative here. And therefore volume is increasing here, decreasing here. So the max volume we can get at small r equal to this big R. So volume is max when small radius equal to square root 2 or 3 big R. Now we need to compute the maximum volume. So we put it in the formula here. Maximum volume is max volume equal to the volume R between 0 and big R, when volume at the point square root of this times big R. So 1 over 3 pi times square root 2 over 3 big R square root big R square minus this term. So I just plug in small r. Now we compute that. Pi over 3 r square 2 3 r square 2 r square 3 2 pi r square divided by 9 r square times 1 over 3. So you can bring r to r. 2 pi r square divided by 9 times r times square root 1 over 3. So 2 pi r cubed divided by 9 square root of 3. This is the maximum, max V. And if we want to get rid of that square root in the denominators, you have 2 pi r cubed square root of 3 divided by 27. This is our final answers.